Hello friends, let us see how asynchronous counter works. See, normally there are two types of counter. One is asynchronous counter, another is synchronous counters. See, asynchronous counters, it doesn't have the common clock to all the flip-flops, whereas in synchronous counter, each flip-flops are having the individual clock. It doesn't mean actually that the flip-flops are not having clock, but in this asynchronous counter, they receive the clock from the previous output of the flip-flop, right? So second flip-flop's clock will be the output of the first flip-flop. So that is what the mechanism in the asynchronous asynchronous counters. Now see, in asynchronous counter, the first flip-flop is having the clock. Now see, I have taken the example of 3-bit counter. We are aware of that one flip-flop can store 1 bit of data. So if I want to have the 3 bit of data, I must require 3 flip-flops, right? So that's why to implement the 3-bit asynchronous counter, I am using the 3 flip-flops. Now it is necessary to understand that, let's say, how much maximum count I will be able to count with this asynchronous counter. So as it is having 3-bit, so here I will take n is equal to 3. If you go for 2n, see, any counter can have maximum states as 2n. Here n is equal to 3, so here maximum count that will have, that will be 8. And what will be the maximum number that we can count? Because when we design the counter, we must be able to know that, right? The maximum number that will be able to count. So that is nothing but it is given by 2n minus 1. 2n we have already gone through, that is 8. Minus 1, that is 7. So maximum 7 that we can count. So we can start from 0 and will go up to 7 number. Okay. So see, normally in asynchronous counters we are using the toggling mechanism. So toggling mechanism we can obtain using either T flip-flop or JK flip-flop. So here we are using the T flip-flop, but you can go with the JK flip-flop also. But you must make sure that all the input should be given as 1. All the input should be 1, because when T is equal to 1, then only according to the truth table of T flip-flop, when T is equal to 1, it goes into the toggle state, and that toggle state we are going to use into this waveforms, right? So let us go to the waveform and understand that how we'll be able to count. See, we have already discussed that maximum up to 7 we can count, right? So it means we are going to start with the 0, 0, 0, 0, 0, 1, then 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, this is 5, 6, and this is 7. So we will start from 0 and will end up to 7. So this is what the outputs of the flip-flops. Okay, now see, as we have first clock over here, so we'll start with that clock and see how this clock is negative age clock, right? Now see, you can have, we need to trigger the flip-flops, right? And we have two types of triggering techniques. So that is, I'm talking about the age triggering technique. Age triggering. So it can be either positive age or negative age. So I'm here using the negative age of the flip-flop. So I'm going negative age. I'm going with the negative age triggering technique. So let us mark all the negative age of the clock. So basically this negative age means 1 to 0 and this is 0 to 1. So your maximum output is, your output here is, see, it is 1 and it is approaching to the 0. So 1 to 0, that is called as negative age. So let us make the output of Q1. See, if I want to draw the Q1, because applying input clock first to the first flip-flop and then it gives us output as Q1. So let us draw Q1. Initially assume that this Q1 is 0. Let's say initially I am assuming that it is 0. Right? It will remain 0 until it has this negative edge. So now it is receiving the negative edge. It means that flip-flop is going to be triggered. And what is the logic? Toggle. Toggle means if input is 0, output will be 1. Right? So if here it is 0, next state will be 1. And it remains 1 till the next negative edge. Right? It doesn't bother about when it comes to the positive edge. Right? It will only change when it receives the negative edge. So here it has receiving the negative edge. So it will again make itself 0. Right? Then it will continue 0 up to next negative edge. Next negative edge, next negative edge, it will again become 1 from 0. Then from 1 it becomes 0. Then 0 to 1, 1 to 0, and so on. Right, so this is what the output waveform for Q1. Now understand that as see for Q1 we have used clock as input, right? And this Q1 becomes clock for the second flip-flop, right? So I am supposed to mark now negative edges of this Q1 because it is going to act as clock for the second flip-flop. So if I want to draw the output of Q2, if I will start again with 0. It will remain 0 till the next negative edge. Negative edge, when it comes, it becomes 1. Remain 1 till next negative edge, becomes 0. Then 1, 0, and up to next negative edge. Now when we receive the Q2 waveform, it becomes clock for the third flip-flop. So I am supposed to mark now the negative edge of Q2 and I will draw the waveform for Q3. It will remain 0 up to next negative edge, becomes 1, remain 1 up to next negative edge, and then becomes 0. Are you getting this? Okay. So now we have marked here, see, Q3 is my MSB. So here when I'm writing all the states, this is my Q3, Q2 and Q1. MSB, you are aware of that it is most significant bit, and LSB stands for the least significant bit. Normally this MSB is at the left side of the all the bits. It is leftmost bit. Okay, and LSB, it is the rightmost bit. Right? It has a lower weightage. Now if you mark here whether we are achieving this count or not, see, till the first clock cycle your outputs were 0 0 0. So Q3 is 0, Q2 is 0, Q1 is 0. So you can write here Q3, Q2, Q1. So in the first clock cycle 0 0 0. Initially it was 0 0 0. Fine. Now in the next clock cycle Q3 is still 0, Q2 is still 0, but this becomes 1. So now you are able to get the output as 0 0 1. In that next clock cycle, if you see 0 1 0, so 0 1 0, so this is 0, this is 1, this is 2, then 0 1 1, that is 3, so this is 0 1 1, this is 1 0 0. So 1 0 0 stands for 4. This is 1 0 1. 1 0 1 stands for 5. And 1 1 0 1 1 1. 1 1 0 1 1 1. So this is 6 and 7. So now when it comes to 7, the counter has to reset now, right? Because it reached up to the maximum state 7. After that it has to be reset. So if you look here, again it has been reset. So then it goes to again reset state and it becomes 0. So again that process will be continued, 0 to 7, then again 0, 1, 2, 3, 4, 5 up to 7, and again it becomes reset. So this is what the designing of the 3-bit asynchronous up counter. But here we have used negative edge of the clock, right? if you go with the positive edge of clock, it becomes down counter. We'll discuss into the next video how to design the 3-bit asynchronous down counter, right? See, these asynchronous counters are also referred as ripple counter because of the way that the clock ripples through the flip-flops, right? Because clock, see, for the second flip-flop, clock is output of the first flip-flop. Third flip-flop, clock is output of the second flip-flop. It ripples from one flip-flop to another flip-flop. That is why it is also called as the ripple counter. Fine. So, as we are discussing the asynchronous counter, let us discuss about the disadvantage, a major disadvantage of asynchronous counter. See, when there is a change in Q1, till that there is no change in Q2. Until Q2 gets some output, Q3 will not get any output because it depends on the previous flip-flop. Second flip-flop depends on the first flip-flop. So they have to wait until they receive, until their previous flip-flop gets the output, right? So time delay is very much high in asynchronous counter. So that is what the biggest disadvantage of asynchronous counter, and that is why we prefer to use the synchronous counter more compared to the asynchronous counter, right? We'll discuss this in deep while we'll discuss about the synchronous counter. Till that time, keep watching the video, guys. Do subscribe and like to the video. Thank you very much.